Today we're going to talk about the Flory full free energy derivation for polymer chains. So last time we figured out our enthalpic contribution, which we see here. We know our entropic contribution from previous videos right here. So we're going to kind of wrap up and basically see how basically the solvent quality will change our RMS, the size of our polymer chain, the scaling as a function of N, and how that scaling changes depending on if we're a good solvent, bad solvent, or theta solvent. So for the rest of this derivation, we are going to move forward and rewrite basically this expression, but we are going to ignore prefactors that are on the order of 1, and we're going to ignore interaction terms that are beyond 3 body interactions. So these guys are automatically canceled out. So if we rearrange this equation, divide out by KT, ignore those prefactor components, we get the following relationship right here. Then we're going to come plug in for our concentration of not polymers, but monomers. So our monomer density, which is, again, concentration is just number of monomer units over R cubed from our polymer chain. Substituting that in, we're able to basically get this expression right here. So now all these terms is a function of R, N, and L. When we want to find the thermodynamic state at equilibrium, what do? We want to find the minimum energy, right? So in our energy landscape, whatever it is, we're trying to find what is our minimum, where is our minimum energy well? How do we find, if this is a plot of G versus some variable R, N, etc., what are we going to do? Well, we're going to take the derivative here, especially because, again, we're looking at the free energy as a function of how long my chain is extended R. We're going to take the derivative of our free energy expression and set it equal to 0. So when we take that derivative of this function with respect to R, we can get this, rearranging a little bit more, getting rid of some of these kind of R values. We get this expression. And then, again, ignoring prefactors, dividing by NL squared. Again, more rearranging, and you could double check this math. And we could also plug in, again, we know this expression for alpha. So you know that alpha squared equals R squared divided by R naught squared, where R naught squared is equal to NL squared, our ideal chain length. Ideal chain. So plugging all that in, setting it equal to 0, we finally get this expression here, which is basically our whole function as a function of L's, N's, R's, and alphas. So excellent. We've done, we figured out how to get this scaling relationship, and now we're going to look at how this expression, what term dominates, and how our end-to-end scaling change depending on if we're in a good solvent, bad solvent, etc. So more on that in the next video. So go back through those notes or those these kind of math, double check it yourself, but you can kind of see now we're going to get some fun stuff in the next video. That's the Flory free energy. Thanks. Bye.